Section 3.4 is velocity and other rates of change. All we're really doing in this section is applying our derivative, or instantaneous rate of change, to a variety of situations. So again, we know that our instantaneous rate of change of a function f with respect to x at a particular value a is this derivative, f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h, provided the limit exists. When we say rate of change, we always mean instantaneous rate of change. If we mean rate of change over a period of time, we would always use the word average. So average rate of change, remember, is the slope, basic slope of a tangent line, of a secant line. Let me get my terms right. So this is our average rate of change of a secant line. If we say just rate of change, we mean instantaneous, which then is our limit as h approaches 0. So keeping those two straight is very, very important as well. So this is review. Remember, one more topic just to throw in so that we are keeping our notation good. If we are looking for rate of change at a particular value a, we're going to put in a number here for a. If we are looking for an equation for the rate of change, we're going to be using x's here. All right, so let's give an example of how we can use this. The area of a circle, this slide was printed wrong. The area of a circle as a function of the radius is a equals pi r squared. We all know that. So first thing we want to do is find the rate of change of the area with respect to the radius. Rate of change of area. So now we're going to start to use notation we're familiar with, but applying it to a particular situation. So again, this means instantaneous rate of change. That means that we are looking for the derivative. So the rate of change of the area with respect to the radius is dA dt. That's what this means, rate of change of the area with respect to the radius. And that's going to be using our power rule. The 2 comes down, 2 pi r. So the rate of change of the area, oh, I don't know why I put a t there. Hope you guys caught me. With respect to the radius, dA dr equals 2 pi r. So there's my formula. Evaluate that rate of change of a when r equals 4. So that means that dA dr evaluated at r equals 4 would be 2 pi 4, which is 8 pi. So that's the instantaneous rate of change of the area of a circle whose radius is 4. All right, let's look at some other examples. Motion. Suppose that an object is moving along a coordinate line so that we know its position s on that line as a function of time t. S is always used as a position variable, so our position equals a particular function related to time. We're talking about distance and time on a graph. The displacement of the object over the time interval from t to t plus delta t, we also call this t plus h, right? Some change in t is our simple change of distance. So displacement is, if this is t and this is delta t, so our, this is t plus delta t. So our displacement is how far did we go from here to here. So if we had traveled 6 miles at t plus delta t and 2 miles here, 6 minus 2, we have gone 4 miles. Pretty straightforward. Velocity of the object over that same time interval now is our displacement over travel time. Velocity over the time interval, that's an average velocity. Now we've put in our difference quotient here. Of course, if we add the limit to that, now we're talking about a derivative. So here it is, the instantaneous velocity is the derivative of the position function with respect to time. So ds dt, dy dx, same kind of thing, we're using new variables here, is the limit as delta t approaches 0. Again, don't be thrown by this. This is the same as our h was. It's just a change, a distance from our initial t value to our secondary t value. So really, as I said, in this section, what we're doing is we're throwing in a whole lot of different situations where we can use these derivatives. So that's the instantaneous velocity, written as a limit. Speed is always the absolute value of velocity. So keep that in mind and pay attention to whether a question is asking you for velocity, found by the derivative of the distance formula, or the speed, which is the absolute value of the velocity. So we've done distance formulas, then we've done velocity. Instantaneous velocity is the derivative of distance. Acceleration is the derivative of velocity. So if a body's velocity is v of t, which we got from the derivative of distance with respect to time, then the body's acceleration, a of t, is dv dt, the derivative of velocity, or the second derivative of distance. So again, a specific application of our derivatives to a specific situation. Let's look at another specific one, free fall. So these two values you should be familiar with. So in English units, feet per second, it's 32. Meters per second is 9.8. Those are constants on Earth. And so this is our formula for distance. So a projectile is shot upward from the surface of the Earth and reaches a height of s equals negative 4.9 t squared plus 120 t meters after t seconds. So there's our distance. We want to find the velocity after 5 seconds. So the first thing I have to do is find an equation for velocity. So v of t is the derivative of s, ds dt, using our power rules. 2 times negative 4.9 is negative 9.8 t plus 120. That's our velocity. So you can see where that 9.8 came in. We threw it upward at a rate of, I'm sorry, and then it's falling at a rate that applies to gravity. My bad. So now that we've got an equation for velocity, v of t equals negative 9.8 t plus 120. We want to find the velocity at 5 seconds, so we're just going to plug that in, and plugging it into our equation, we get 71 meters per second. Okay? All right, so again, sensitivity to change. When a small change in x produces a large change in the value of the function. In other words, if I'm going from here to here, and that's a small change in x, if I get a large change in the function value, we say that the function is relatively sensitive to changes in x. F prime is this measure. So even if this weren't a straight line, if we did something like this, F prime tells me how quickly the graph is changing, or its sensitivity to change at a particular point. So if F prime is large, we have a high sensitivity to change. So that ties into economics. Economists have a specialized vocabulary for rates of change in derivatives. They call them marginals. So if you hear that in an economics class, it's just rate of change. In a manufacturing operation, the cost of production is a function of x, the number of units produced. So C of x gives us a cost per unit. The marginal cost is the rate of change of that cost, so it's dC dx. Sometimes the marginal cost of production is loosely defined to be the extra cost of producing one more unit. So how quickly does our cost change as we add more units for production? So here's an example. Suppose that the dollar cost of producing X washing machines is this function. The cost, dependent upon how many machines I'm producing, will go up or down. Find the marginal cost. All that's saying is find our derivatives. So the marginal cost is C prime of X, which is 100 minus 0.2x. That's the derivative. The derivative of 2000 is 0. The power here is 1. That comes down and we lose the x. And then the 2 comes down to multiply and we reduce the power on the x. So there's my formula. So the marginal cost of producing 100 machines, plug in 100 to this equation, and we end up with $80 per machine. Okay, and that's it. As I said, several examples of applying our derivative to specific situations, and we will be working on these in class, obviously.